Good morning, guys. This is a continuation of the elimination method, my first video on uh, the conversion from a matrix to an upper triangular form. And this is just an extension of the method I introduced on my first video. So the second method here that I will be presenting is known as the Gaussian elimination. And the Gaussian elimination has the objective of avoiding the possibility of obtaining very large coefficients. So in our first lecture, we take note that our multipliers are very dependent on the numbers, no? On the uh, uh, pivot row, okay, on the diagonal, and also on the column values under the pivot. Hence, if these are very large, and upon doing a very large order of a matrix, then our computation will actually be very heavy, no? Because we will be obtaining very large coefficient. So in that regard, the Gaussian elimination avoids this complication by simply using a different multiplier, which is actually the ratio, okay? This is the multiplier that the Gaussian elimination is using. Okay, so this is the ratio of simply the value, okay, of the cell, the value of the cell under the pivot AJJ. Okay, so AJJ here is the pivot value, and AKJ is actually the column under or column below the pivot value. So if the pivot value is 0, meaning to say that the diagonal values of the matrix has a 0 entry, then there is a danger of misbehavior by simply doing a division by 0, which yields to an overflow. So this can actually be remedied, as I have said on my first video, by simply switching the rows to avoid 0 values on the diagonals. Okay, so this multiplier is actually multiplied to the jth row from the succeeding k rows to make a transformed numbers in the jth column equal to 0. Okay, we are subtracting this from the succeeding k rows to make the transformed numbers in that jth column vanish, and proceed similarly for the rest of the columns. No? So take note that the k here is actually a derivative of your j plus 1 counter, no? So which is actually one row ahead, no, of the jth row. So we now apply the procedure in the previous example 1.1 for us to better understand the difference between the basic elimination method which I presented and this Gaussian elimination procedure. So again, we have here the same augmented matrix AB. So this is the separator separating the coefficient matrix with the vector of constants here. So for the first cycle, as what we have done on the previous, we simply make use of multipliers, but this time, instead of having a multiplier on the row to be operated on, we only seek a multiplier to the pivot row that we are taking into consideration. So here in this first cycle, your pivot will start at this first diagonal. Hence, our multiplier will simply be equal to a k, okay, j, which is the jth column, the first column, and this k is actually the j plus 1 row. Okay, so we add one row from the first column to the second. So this is simply a negative. So okay, so this is now your j plus 1, or simply your k value. Okay, so this is now a k j. So this is my j value here, which is 1. And my k value here is simply 2. So this is now my a 21, which is minus 3. Okay, so this is a 21 divided by ajj, which is a11. Okay, so this multiplier here will be sufficient to satisfy our objective of zeroing the value, no, of the cell under the pivot, okay, which is actually this. So by simply doing this here in this second row, the row of concern, the row wherein the operation is being done, then we achieve a value of 0. And the rest, of course, will change. So this is our new row vector A 2j. Okay, A2 means A, row 2, column J. So these are all columns, J1, J2, J3, and J4. Of course, J4 here is the augmented, okay, vector of constants. And doing the same thing, okay, so we just get, okay, AK J, which is this one, 1. Remember that K here now becomes 3 because our counter J is now on the okay, on the succeeding J plus 2 here. Okay, so this is 1 over, still the pivot is fixed because this is the pivot, we don't change it. So still J equals 1 there. So 1/4 of the pivot row, you call this now the pivot row, and subtract that from the row in operation where the transformation is being done, and that's R3, and will yield the same 0 under the pivot. Okay, so the first cycle zeros out, okay, the values of the cell under, okay, under the pivot. Okay, so this is now my new second and third row, which will yield with a result, okay, of the resulting matrix now becomes this one. So this is my new new row 2 and new row 3. Of course, the row 1 here is still the same. And my new or the updated matrix will simply be this one here. Okay, so take note that the values there will now be different from the values obtained from our first method. Okay, but this does not mean that the operation on the system of equation will yield different results. It's only the equivalency of the the coefficients that changes, because we need to know the fact that in our elementary row operation we can simply multiply each row by any factor for as long as the whole equation representing uh, uh, represented by that row is not changed. Okay, so for cycle 2, our pivot shifts from j equals 1. Okay, so this now j equals 2. So our pivot is this one, the diagonal. So the diagonal determines the pivot value at the pivot row and the pivot column. Okay, so jj is simply negative 2.5. Okay, so this is now our A22. Okay, and my K, okay, my AKJ is simply A32. Okay, so this is my A32 or AK2 AJJ. So AK2 is negative 0.5 and JJ A22 is negative 2.5. So this is now multiplied by the pivot row. So this is my pivot row. Okay, R2. Okay, so this is the row 2, and then subtract it from the row being operated upon. So this row 3, which will yield again a 0 value under the pivot, always under the pivot. So our target is to zero in this because it's already 0. There will no be change. There will be no change anymore in this because the calculation will all remain 0 here. Okay, so this is now 1.8 and 5.4 is now our new row 3. So this new row 3 will update the row 3 on the first cycle such that the resulting matrix now becomes this one. So this is our newest rows and matrices. So this is the newest R3 here. Of course, this is just the same as that one. No? So the above matrix is now an upper triangular matrix. However, if we had stored the ratio of the coefficient or the multipliers in place of the 0 values as shown in the parentheses, our final form will be this one. Okay, so these are the multipliers that we use. Okay, our multipliers that we use in the first cycle, and this is the multiplier that we use in the second cycle. Okay, this is the upper triangular matrix as was obtained, and these multipliers actually represents the pair of the lower triangular matrix in which if we are going to multiply this lower and this upper triangular matrix, we then achieve, okay, so this is the lower matrix and this is the upper matrix, then L. Okay, this is now our L and this is now our U. Of course, if we want to make this constant, we have to place 1, 1, 1 there, no? Because these are zeros there. We can just place, we're just adding it, okay? We can just place negative 0.75 here. Not adding, but multiplying it, okay? So multiplying this as my lower triangle and this is my upper triangle will actually be yielding the result of your coefficient matrix, the original coefficient matrix. Okay, so the coefficient matrix, original coefficient matrix, can actually be represented by many pairs. Okay, so this is only one of the many pairs of the lower and the upper triangular matrix, because we have seen from our first elimination method that our upper triangular matrix is different here. Okay, this is a 4, negative 2, 1, minus 10, 19, and then negative 72, but here it's different. Okay, hence this pair is only true or consistent if we will be using the technique presented here as the Gaussian elimination procedure. If we do a different technique like this one here, we will be yielding as many pairs as we want, simply because we can do a lot of changes in our value of multipliers here. Okay, but still the system of equation is consistent, because if we multiply L times U, we will be yielding with the original matrix coefficient. Of course, here in the multiplication, we are only referring to the coefficient matrix without the augmented vector of constants involved. Or simply, your matrix A is simply L times U, and this procedure represented above is called the LU decomposition procedure. So from the above example, we can see that the Gaussian elimination does the following, which are very worth remembering. So it solves the system of equations. Okay, sorry for it computes the determinant of a matrix very efficiently. Okay, so because if we have an upper triangle and the lower triangle, it's very easy to note that the determinant is just the product of the diagonal, because these are all zeros. So this is the product of this 1, 1, 1 is 1, and the product of this will be the determinant of the matrix. It can also provide us with the LU decomposition of the matrix coefficient, in the sense that the product of the two matrices L times U may give us a permutation of the rows of the original matrix. Okay, so permutation means a lot of groupings and pairs can be derived from the lower and upper triangular systems that we have obtained from the Gaussian elimination procedure. So thank you very much for listening. In the next video, I will be giving you a procedure on how to develop a simple program on Gaussian elimination, basically using MathCAD Prime 4.0 as my platform. So I'll see you in the next video. Thank you very much for listening.